I'd like to wish everyone a warm welcome to our first afternoon session today concerning the corrosion of high entropy alloys and or multi-element, multi-principal element alloys is perhaps a more general term. And as I'm sure most of you know, these materials have received considerable attention for their physical properties in recent years, but are much less well known for their corrosion and electrochemical properties. And it's my hope and my wish that this short symposium this afternoon will contribute something to the discussion on these properties and or germinate some ideas on these properties. Whether or not that wish will come true, one thing is for certain, is that our three keynote speakers today have made considerable contribution to this area of research. And so we're very, very fortunate to have Nick Birbilis, John Scully, and Jerry Frankel to present their work and their insights into this field. And following that, we will have two younger scientists who have been working in collaboration with other laboratories, one with John Scully and one with Northeastern University in China, and have been working to some extent in my laboratory in Paris. This will be Dr. Junsoo Han and Dr. Xuejie Li. And with no further ado, I will turn this over to Nick Birbilis, who is obviously I cannot possibly give a real introduction for Nick, because reciting his curriculum vitae would take up the entire time we have for his presentation. But he is Deputy Dean at the College of Engineering at Australian National University. And I give it to you, Nick.
Thank you very much, Kevin. And I really appreciate the opportunity to be involved in this first meeting, which has really, by all accounts, turned out tremendously well, and a nice way of pulling people together during a pandemic. So what I thought I'd do, I'm the first of 5 speakers, and actually there's a couple of plenaries after me, but everyone coming after me is heavy hitters, including Junsoo and Xuejie. So I thought I'd introduce with a bit of storytelling and maybe lay some of the basics for some of the others to build upon. Back when providing an abstract, like many of us do, I punted on a topic which was corrosion and passivation of lightweight aluminium-based MPEA. So I'm going to have to stick with that, unfortunately, and I'll try not to deviate terribly much. But before I begin, I'd just like to acknowledge, as we normally do here in Australia, the traditional owners of the land on which I'm currently on, which is the Wurundjeri people's land, and pay my respect to their elders, past and present. These are some of their traditional symbols. And throughout the presentation, I'll acknowledge the tech support and the researchers as I go along. But in order to start at the very, very beginning, this particular session covers multi-principal element alloys, but I thought I'd give a bit of notation for those, but that are maybe perhaps less familiar. So starting about 20 years ago, high entropy alloys started to become quite popular. And these particular alloys were characterized by equiatomic alloying additions of about 5 elements usually, and a high entropy of mixing. And it turned out that after some amount of time, a different notation called complex concentrated alloys or compositionally complex alloys evolved, because many times when people tried to make high entropy alloys, they turned out to be multi-phase, not single phase, so sort of violated this high entropy aspect. So in that particular case, you can have more or less than 5 elements, and entropy doesn't matter so much. But more generally now, we have multi-principal element alloys. And here, a little bit more anything goes, provided where n is greater than 1 for the principal element. So unlike high entropy alloys or CCAs, you may not have equiatomic proportions of your elements. You may only have 2 or 3 elements that are there in principal proportions, and then a whole range of different other elements. It turns out that actually this is a rational notation because it overlaps with current existing alloys that are currently in use at present. there are some multi-principal element alloys that have been around for a very long time, particularly in the nickel alloy family. And of course, as Kevin mentioned before, the number of publications has just gone boom in the last decade for these particular alloy systems. And it's not surprising when you look at the physical properties. Okay, so if you look at the physical properties of these alloying elements, in the top left, you'll see extreme hardnesses. This is from a review from the team that Peter Liao works with some years ago now. And on the bottom right, you'll see extremely high yield strengths. But what's interesting is these yield strengths are really coupled with high densities. So therein lies a little bit of a challenge and the genesis of my topic of presentation, which is how can we do this with lightweight or more lightweight alloys. So in terms of the storytelling, I became very interested in this system about 11 years ago, back when I was at Monash, where we would produce many alloys using casting or selective laser melting or direct laser deposition, spark plasma sintering or arc melting. We got fascinated by these alloys because we had a hope that we could produce net shape large high entropy alloys by additive manufacturing. And of course, that was the goal. And we've been attempting it ever since. But contrary to high entropy alloys, this is where I started using the term CCAs, like a lot of other folks in the United States, particularly Hamish and Fraser and other groups at Ohio State and elsewhere. They ended up, and we ended up making multi-phase alloys, contrary to trying to make single-phase alloys, even when using equiatomic proportions. And so like any good corrosion group or even bad corrosion group, when you make samples, you want to start doing corrosion testing at some point, or someone wants to do corrosion testing. And fortunately, we found some other early collaborators at the time, including B.S. Murthy, who was at the time at IIT Madras and is now I think running the whole university at the Indian Institute of Technology at Hyderabad. We shared a whole range of alloys, many dozens of alloys, and we started doing polarization testing. And I'm going to cut a long story short. What we found is not what we expected. We found extremely huge windows of passivity for a whole range of alloys. Now, I've just picked these ones because what was amazing here is not so much that an alloy with titanium and chrome and nickel or something will give you a huge window of passivity, but coming from a background of steels, then aluminium alloys, then magnesium alloys, heterogeneous microstructures were generally known to be evil. So we started finding huge windows of passivities, even with multi-phase alloys. And then we saw that again, you know, with different alloys. I'm just going to try and move stuff on my screen here so I can see what I'm looking at too. Different alloys. And then with different alloys, again, including some very odd ones, and then with more and more and more alloys, even those that were 3D printed by directed energy deposition or direct laser deposition, as you can see here. So this actually gave us a little bit of inspiration to say, well, look, if we can only make multi-phase alloys in this high entropy type family, so CCAs, maybe we can just actually tip our hat to these lightweight versions and see what we can do there, because it looks like everything's going to be corrosion resistant, more or less, with some of course exceptions, but it was generally the case. So in terms of making light high entropy alloys, if you think about the alloy production and the safe and rational way in which you can make things in environments while maintaining human health. If you take iron as your baseline and then identify the elements that have a lower density than iron, and you remove those that are going to blow the laboratory up or kill people by toxicity, you take away all the red stuff, because that's not good for human health. You take away the blue stuff, because that's gases, and then you take away the sort of gray shaded, sort of what looks like dark green, but gray shading stuff, because that's heavier than iron. So actually all you're left with is not very many elements to make light CCAs or MPAs. And PhD student Yao Chu ran all these through the empirical laws for designing high entropy alloys, worked out densities, all the different empirical parameters, which I'm going to skip over, but I can be contacted after this and make them available. And he shortlisted it down to a small number of alloys and then a final system, which was a 4-component system that had a high entropy of mixing, should be single phase with a very, very low density, or at least very low compared to steel. So here's Yao here on the TEM where he did most of his best work. And it turns out that when you make this alloy, and you can make it by many means, we typically made it by arc melting, it actually was a single phase alloy. Turns out we did a heck of a lot of characterization, which I'm going to skip over, but it wasn't a single phase BCC alloy. It was a B2 alloy, which for those that don't know is an ordered BCC alloy where the location of the atoms is defined. So there's some ordering. So it turns out that the body-centered atom in these alloys was always aluminium, and for the corner positions, titanium and chromium would always be in a heavy fight for the corner positions. That doesn't matter so much here. But what's interesting about this alloy, and now we move to some work that a current PhD student, Xuejie has been doing, is that it's extremely, extremely corrosion resistant. And I'm not going to talk about the family of these aluminium, titanium, vanadium, chromium alloys because we've expanded into looking at the family. I'll just talk about this sort of archetypical alloy. But in spite of pH, very, very corrosion resistant, the hysteresis suggests very, very rapid repassivation as well of this particular alloy. So then the logical thing to do is to ask the question, well, how do we rationalize such corrosion resistance? And then subsequently, what is the surface film? Now, I don't want to teach anyone how to suck eggs here because Kevin, our chairperson, is the inventor of this particular method, which is the atomic emission spectroelectrochemistry method, which can also be done by mass spectroscopy as well. So mass spectroscopy as well. This involves using a flow cell and looking at the dissolution of your sample in real time using either atomic or mass spectroscopy down the end, where you can actually look at atom by atom dissolution, right? And I'm not going to jump into that too much, but it actually turns out that I believe all of our speakers today are presenting something that involves this technique at least once. And that is not because it's a racket and you can only study this system these systems if you use this technique. It turns out that this technique has made it possible to study this alloy system in ways that couldn't have been done before, or that would have left us not knowing what the heck was going on. So it's quite clear, again, I'm going to cut a long story short, that we get incongruent dissolution. So that means non-stoichiometric sort of dissolution of this particular alloy as you polarize it. So what you see on this curve is you see the red line, the red solid line, is the current that you measure from your potentiostat, and these other lines here are the contributions that come from titanium in pink, aluminium, vanadium, and chromium, and the total dissolution current measured by, in this particular case, the spectrometer in black. So it turns out that you get more dissolution of vanadium and chromium in the system, and then their transpassive dissolution actually occurs at some rate, significant relative to the other elements, because this is a log scale. So then when you look at XPS, again, I'm going to cut a very long story short here, and it turns out that you actually have a multi-oxide film on the surface. And this has been done at different grazing incidents and so forth as well. I'm not going to show all that information, but the composition of the film also changes as you polarize anodically. You get more and more titanium in your film. It's principally an aluminium oxide film. But what's really, really interesting, if you haven't heard me say this before at other talks, I'll say it again, is the real interesting thing for us was the very high proportion of unoxidized, so zero oxidation state metals in the film, which is really, really unique relative to, I guess, single principal element alloys. So having unoxidized metal in a film, we think, is a significant characteristic of where these particular alloys get their corrosion resistance. It also turns out that the thickness of the film changes as you polarize it anodically, and you get a continuous evolution of the film composition. I'm not showing you sputtering XPS here, but these are highly complex oxides. The incongruent dissolution is obvious, and you have a lot of unoxidized metal present. In this particular case, we've applied analysis where you do staircase type signals, and it turns out that you can calculate the barrier layer thickness and so forth from electrochemical techniques that are consistent with the point defect model. And it turns out that this high entropy alloy and others, or multi-principal element alloy, I should say, are consistent in their behavior with the point defect model. The growth behavior changes with the evolution of the film composition. The thickness of the film increases linearly with anodic potential and logarithmically with time. So interesting behavior. Over a presentation, it's impossible to get you folks to grok what this is, but this is a cartoon actually that was heroically put together by Sebastian Thomas to try and rationalize a multi-oxide film with unoxidized metal in it and try and sync up what's actually going on in these films with the point defect model. And again, to cut a pretty long story short, because I want to cover a bit of storytelling here, it turns out that there's particular features that we believe give rise to corrosion resistance in these lightweight MPEAs that we believe can be then transferable more generally. And so I'm going to finish off by a couple of really short examples in the time that I've got left. And this is, again, a lightweight MPEA study in collaboration with Dr. Rajiv Gupta at NC State University on a project with the Office of Naval Research. So I say, are they here to save us? I'll explain what I mean by are they here to save us at the end. But if you can get corrosion resistance by having, as we've seen before, multiple phases, a hodgepodge of elements and so forth, you may as well take this situation by the throat and try and make something that's quite or very lightweight and that actually just uses commodity, so non-passive materials. So if you take iron, manganese, aluminium and silicon, basically things that you can find in a junkyard, you know, from wheels, engine blocks and so forth, and then put them together, what actually happens? Well, it turns out that Sean O'Brien, the PhD student, made this particular alloy. He's made it many times in similar alloys many times by arc melting, is that you get a significantly lower density than steel and a tremendously high Vickers hardness in a multi-phase alloy, and you get a tremendous window of passivity. Quite remarkable. Actually, this even had me floored. And then, of course, the same questions arise. Why, right? So this is where atomic emission spectroelectrochemistry comes into it. And of course, XPS also comes into it as well. So when you're doing your spectroelectrochemistry, and Sanjay did these runs, you could see that there was again incongruent dissolution. And it turned out that the most reactive element in this particular alloy was silicon. And silicon dissolved at much, much higher rates than the other elements. XPS confirms this. This particular data here shows the cationic fraction in the surface film by using angle resolved XPS, and it shows that there's much more silicon in the film as opposed to aluminium, manganese and iron, which one normally thinks of as the least corrosion resistant element, perhaps in this ensemble of elements, actually was being oxidized at the lowest rate of all. And so nothing tells a story like a good cartoon. So in this particular cartoon, this shows the mechanism by which corrosion resistance is imparted to this alloy. It's a dynamic passivation that actually happens by a small amount of dissolution promoting silicon loss, so silicon dissolution, which is then followed by precipitation as SiOH4, which is a common product from the dissolution of silicon dioxide in the presence of water as well. And it's this particular phase on the surface film or in the surface film that provides excellent passivity of this alloy too. So something that is a different way of thinking about passivity. Dynamic passivity, kinetics are important. And clearly we're getting to understand these particular alloys in ways that we couldn't previously because of methods like spectroelectrochemistry. So based on what we know so far, this is my last example before I run out of time. how can we design and do so quickly very useful multi-principal element alloys? Because the two examples that I've given were hydraulically designed. I say that sort of half jokingly, but hydraulically designed using using a lot of nous and so forth. So this is where machine learning could potentially come into things and use objective-oriented design. So we've developed with a new PhD student, Zhipeng Li, a model that we're calling Cardigan, which is the Compositionally Complex Alloy Research Directive Inference GAN, which is a generative adversarial network for design and discovery of multi-principal element alloys. So I want to show you something different other than corrosion in terms of the design of these particular things. Now, the reason why we used a generative adversarial network, I'm going to go quick because I know that time is running out, is because separately to other machine learning models that are based on a lot of data and data science, there's actually a very small number of existing alloys reported in the literature. We found only 278, which is perhaps even more than you would think. So there's 101 solid solution, single phase solid solution alloys, some mixed phase, and then some other ones with secondary phases as well. That's not enough for creating a machine learning model. So for those that have heard of GANs before, what we did in this particular case is we generated synthetic alloys and used a critic or a discriminator to discriminate those synthetic alloys so that we could generate a very, very, very large data set that was moderated by the empirical rules for alloy design and what was learned from the smaller database of actual data. These are the empirical parameters and their calculation. It turns out that from 200,000 samples, 3,809 samples were selected as candidates for novel single-phase multi-principal alloying elements. Now, from these, 188 candidates were selected with a density less than 8 grams per centimeter and an alloy cost less than $12 US per kilo, which is really, really interesting. So here you see the reams and reams of alloys that have been developed by machine learning. And here you can see the price versus the density. That should say density, it says density. And you can start to pick some of these and think they're the ones that I'm going to start to probe a little bit further. And this is work in progress, but we did try this recently, and here's an alloy composition that's lightweight, again, a little bit of a hodgepodge, but with a focus on commodity elements like aluminium, copper, and iron to generate a single phase alloy that's FCC in the hope for some ductility. And so this is completely computer generated. There's nothing intuitive about doing this. And if you were to ask a metallurgist what's this going to make, they probably couldn't tell you. But we made it, and guess what happened? It turned out, if you think you know the answer, it turned out, was it FCC? Turns out it was FCC, single phase. We thought it was going to be single phase FCC, but actually it had two phases and both were FCC, which I think is really funny because these MPEAs are already showing us their good sense of humor and indicating that they can outsmart us even when we're trying to outsmart them. So with that, I've run out of time, but an obvious concluding remark is that multi-principal element alloys are really interesting and awesome. We've not scratched the surface, nowhere near it. Like I said, there's only 278 well-reported ones in the literature to date, in spite of there being a massive run-up over the last decade. Composition is key. So talking about corrosion, composition is key because every constitutional element contributes to the passivity of these particular alloys. Even though many of them are passive, in fact, most of them are passive, they have a different underlying or a different kinetic mechanism to that passivity. There's a continuous evolution of the passive film that's coming from incongruent oxidation and dissolution, which separates MPEAs from pure metals and single principal element alloys. And therefore, that's why advanced characterization approaches are actually essential to understanding the corrosion behavior of multi-principal element alloys. The good news, though, is that a mass spectrometer or atomic emission spectrometer is much, much, much cheaper than things like SEMs as well. So this could also be a great renaissance for electrochemistry as a high resolution method, because actually electrochemistry is one of the highest resolution methods out there in terms of the currents that you can measure. I do genuinely think machine learning is going to have a big role to play because it's going to extend to digital manufacturing. And we've seen, and I even showed it at the start, and this is an old result, that multi-principal element alloys are actually amenable to additive manufacturing, and that leads to objective design. So with that, I thank you all, and thanks to everyone for being on the line. I see huge participation here, so extremely humbled. If anyone wants to reach out to me, those are my details, please do. So Kevin, I think I'm going to pass back to you.
Okay, thank you, Nick, for a brilliant presentation of clarity that is remarkable as always and extremely inspiring. I cannot imagine a better presentation just to introduce this subject matter. So thank you once again. We do have a couple of questions that are in the Q&A box here. So I will read them to you. The first one is from Andreas Hein. Forgive me if I'm mispronouncing your name. Aluminum, iron, manganese, silicon alloy seems to have pretty high currents in their passive region of some microamperes per centimeter squared as compared to SS316, stainless steel 316, which is usually lower than 1 microampere per centimeter squared. Could that mean for applications in different media or atmosphere, since the ions leaving the material must go anywhere? Question. Or is it just a measurement artifact of dynamic polarization?
Yeah, really good question. So there's two answers to that, but well done, Andreas, because you're clearly a very astute reader. So it turns out that the currents are not much higher in the passive region, so it's always hard to read off the log scale. But it turns out that of course what matters for bold exposure is the currents that you're getting at open circuit, which are really low. So fortunately, we don't expose materials to environments in a polarized condition. That can happen if your material is galvanically coupled. But yeah, the corrosion rate and the passive current density are not always necessarily linked. So we can take that discussion offline, but really astute viewing. And in fact, I'm proud that someone's paying such attention. Really good question.
Okay, we have 2 other questions. I appreciate, Nick, that also your remarkable presentation was also perfectly in time. So we'll try to keep the answers kind of short. I think these questions are fairly straightforward. Zahid Galishka asked, thanks for the presentation. What does represent the transition in thickness observed in thickness versus time plot?
Yeah, really good question. I didn't care, you know, in the old days when I worked with reactive metals like magnesium, I also didn't care about thickness versus time plot, but it turns out that there's a whole community out there that are passivity buffs, and you've got a couple of legends coming up after me. And it turns out that the film growth kinetics are actually really important in terms of understanding passivity. And there's a number of models out there that you can pick from when you want to, I guess, classify the sort of passivity that you're seeing. And the different models are discriminated on the basis of their film growth kinetics. So the reason why I showed it is to show that we have logarithmic film growth kinetics as a function of time, which doesn't occur with a lot of passive film models. So basically that was my polite way of saying a lot of the models previously presented are junk and focus on the ones that mimic the kinetics. So I was trying to be polite about what model to use and what not to use. The last one I can probably take quickly, it's about wear resistance of MPEAs. Yes, the wear resistance is very good because they have high hardness, but that doesn't mean game over. Turns out that they actually often have low elongation, which is a challenge as well. So high hardness for wear is good, but in terms of full portfolio of mechanical properties, MPEAs are not always there yet, which is why hunting for face-centered cubic variants is preferential. Cool.
Okay.
Probably said enough, Kevin.
Thank you very much, Nick. And we will pass the word over to our next speaker, which is Dr. Joe Frankel. who is the Distinguished Professor of Engineering at Ohio State University and Director of the Fontana Corrosion Institute. So I will pass the word to you, Jerry.
Thank you very much. So yeah, I'm really pleased to be joining this group in this conference. It's kind of the silver lining of this pandemic is to have the opportunity to develop these types of approaches to communication and interaction, where we have people gathered really from around the world and being able to talk to a whole bunch of people we wouldn't normally get to talk to. So thank you so much. Okay, so yeah, I'm going to talk today about some similar alloys here. Again, we're calling them multi-principal element alloys, MPEAs, and we're not focused on the equimolar concentrations. And I'll talk about the elements here that and why we focused on that. This is, unlike the previous two speakers, I'm going to limit to really one project here, not give you a full rundown on everything that we're doing. I'm going to talk about the work of Anoop. Anoop Panindre is a grad student working with me, and this is largely his work, and there he is. Thank you to Anoop for all your good work. And except for a brief mention, I'm going to again focus on this project. It's an ONR project that I want to acknowledge support of, and also the NSF for the XPS. And the material that I'm going to discuss, it has been just published in the Journal of Electrochemical Society. It is open access, which JES does quite well, so you can go to that and find it. Okay, so just as a matter of introduction, we started with this alloy. We're calling it MPEA1. Okay, and John Scully already introduced you to it a little bit and showed you what great properties, what great passivity it had, and he showed some of the atom probe tomography results. Didn't really dwell on them, but talking about the oxide, which is a non-stoichiometric solid solution oxide enriched in chromium, but containing all kinds of other elements shown in here. What I am showing you on these polarization curves are for both the as-cast material and homogenized. So these are arc melted buttons that we have tested, again, either as cast or we hold it at a high temperature to make sure it's well homogenized. And you can see we're testing in a range of chloride concentration up to 12 molar HCl. So 12 molar HCl is what you get out of the bottle. And 6 molar HCl might represent the concentration that would exist in a local pit environment. And you can see that these are passive, spontaneously passive, and even giving pretty low corrosion rates in this 12 molar HCl, though kind of active dissolution in that environment. I'll tell you that the as-cast, again, I'm not focusing on this alloy, the as-cast is indeed a single solution FCC, although it has dendrites and coring, so there are compositional gradients. Nonetheless, this alloy is extraordinarily corrosion resistant. Okay, so this was the work of that program called WASTE PD, the Energy Frontier Research Center, and that program had no intent of coming up with any practical alloys like our recent questioner mentioned. And indeed, because of the high ruthenium content, it would be extremely expensive if you consider the cost of the raw materials alone. So yeah, not practical. But again, that wasn't the point. The point was to explore the behavior of these kinds of alloys. So in this work, we're looking at replacing ruthenium. Okay, and starting with this MPEA1, okay, and substitute with commodity elements. So it's related to what we've heard from the previous two speakers. And the goal is to have a large single phase region at some high temperature that will allow for solutionizing. And guiding us has been this work from Philippe Marcuse that's already quite old, 25 years old, but we think it's quite insightful, where he talks about alloying elements being either passivity promoters or dissolution moderators or blockers. And this is a plot of the adsorption enthalpy for oxygen, oxygen adsorption on the surface. And this is a measure of the metal-metal bond strength. So if we have a high metal-metal bond strength, that might prevent the dissolution from taking place. But if the metal-metal bond strength is low, but let's say the metal oxygen bond strength is high, as we know from these strong oxide formers, that would promote passivity. And Philippe suggests that we should have a balance between those. So the approach that we've taken is, again, not unlike what we've heard from the other speakers, but we're started with our MPEA1 and substituting in elements. These 5 elements are the usual suspects of the commodity elements that would go in. And we use thermocalc to then look for where these what alloys in particular would have these ranges. Here were these wide compositional single phase ranges we're interested in to be able to solutionize. Okay, and so you can see, I'll show you the compositions we ended up with, but each of them has such a wide range. And you'll note that at lower temperatures, all kinds of phases are predicted to form by thermocalc. And in fact, a major thrust in this work is to try and strengthen these materials by first solutionizing and then heat treating in a region where we would expect to precipitate these other phases that could be hardening. And I'm not going to talk about that work, but indeed we can form very interesting phases, very interesting microstructures by that route of solutionizing and then heat treating at lower temperatures. And Nick talked a little bit about the ability to have multi-phase structures that are corrosion resistant, but actually what we find is more or less what is expected, that these types of multi-phase structures lead to a degradation in the corrosion performance. Again, I'm not going to talk about it, but that is where the focus is. All right, so again, with our starting composition of MPEA1, which has nickel, iron, chromium, a fair amount of molybdenum, a bit of tungsten, and then this ruthenium, okay, which has the very high cost. We've developed these 5 different alloys. We call them A1 through A5, and then with the subscript of the element that is replacing the ruthenium, just to remind you of that. Okay, so you see that these alloys aren't exactly, they aren't exactly this MPEA1 with ruthenium exactly replaced by these elements, but they are, with some tweaking to allow this wide range of solid solution expected at higher temperatures, we've ended up with these alloys. So you can see that for nickel and iron, they only have 5 elements, where the nickel concentration or the iron concentration has been increased and the ruthenium has been removed. And then you see we've added manganese, aluminum, or copper in these other alloys in A3 to A5. Now I'm presenting here these metrics that Nick flashed through, and I won't spend much time on them either. This entropy of mixing, I don't think that anyone is these days thinks that high entropy is critical in the corrosion performance at all. but indeed this 1.5 R is reached only by a couple of these alloys. We have the valence electron concentration, which has to do with the ability to form a solid solution, the average atomic size mismatch, and this omega, which relates the entropy and the enthalpy of mixing at the melting point. And this electronegativity difference, and I'll talk about those. To answer the question raised by that previous questioner for John, you can see the prices here are about twice those of 304 stainless steel, but a small fraction of the MPA1. Okay, so we, like those other alloys, we arc melted them, casted up buttons, and indeed there's single solution FCC structures, and that's predicted based on this valence electron concentration being greater than 8 and the lack of phase formation related to the atomic size mismatch and this omega factor, which from this work by Tsai is in a range where we would expect the solid solution formation. So here I'm showing the Vickers hardness related for the solutionized materials. Again, I'm not showing what happens when we can harden them by precipitation of phases, but indeed the solid solution strengthening provides some added hardness relative to, say, 304 stainless steel, and it seems to correlate with this electronegativity difference. Let's look at the corrosion of these samples. So these tests were done fully immersed in 3.5% sodium chloride solution. Okay, and what we see again, these are the 5 different alloys. I'll tell you that the MPA1 exhibits no susceptibility, as I showed only the upward polarization curve previously. So what we see is that when we use nickel or iron to replace, we get essentially transpassivity with a small amount of positive hysteresis coming out of the transpassive region. And in fact, we get some cosmetic corrosion, some small extent of attack. These other alloys, the ones with manganese, copper, or aluminum, are susceptible to crevice corrosion, the masked region being shown, separated by these lines. And we can see that this was using a black wax masking. And I'll tell you that these alloys are, this is also, I should say, this is the as cast A alloys, not the solutionized A alloys, which again will promote the tendency for this to occur, but they're very, very susceptible to crevice corrosion. And indeed, it's not easy to eliminate the crevice artifact. One approach that we've taken is the syringe cell. So John talked about a droplet cell. This is also work that was led by the efforts of Anoop and published a few years ago. This is a very simple approach to creating a droplet, and it allows you to make very easy measurements in the absence of a crevice, because we just have this droplet you can see here. It's basically a simple syringe where the plunger is removed and the gasket perforated to insert a reference electrode and a counter electrode. And this is, again, with this lab jack, makes for very easy measurements. And in fact, the approach is very similar to some microcell approaches, except the intent is not to have a microcell area, although the area will vary with the size of the syringe. You can use large syringes and have relatively large areas, but the droplet eliminates the crevice. And it works quite well Here you see these alloys. These are now solutionized, but in this syringe cell, we can see that there is really no crevice that formed. So these are all of these alloys in the 0.6 molars, 3.5 weight percent. Okay, and you see, some, again, small hysteresis coming out of the transpassive region. The manganese alloy is exhibiting considerable metastable activity, which is going to need some more work. But all of these are spontaneously passive, and no evidence of pitting or crevice corrosion in this chloride solution. So they are, if you can eliminate a crevice effect, extremely resistant to pitting corrosion at ambient temperatures. We took an approach that has been promoted by John in this paper with Nick, our previous two speakers, in fact, to look at the current decay and to measure the impedance at a fixed frequency during that potentiostatic hold. And this expression, which can be found down in this paper, is a way of estimating the passive film thickness as a function of time. And we can see that all of them are exhibiting a nice passivity in the passive region, and they all give us, from this estimation, give us film thicknesses that approach a few nanometers, which would be expected for these types of passive materials. So we haven't yet taken the spectroelectrochemistry approach to studying these materials, but have done XPS. And in fact, we see that there is chromium in the passive film. This is the natural air-formed oxide. Here's the passive film. Okay, so this air-formed oxide, rather enriched in chromium. Passive film, not exclusively chromium. Say all of these elements, iron and nickel, are participating in the passive film that's formed. And so I would say really no dominant cation in these different alloys. Further analysis suggests that if we've done a lot of different analysis. One thing that comes out of this is that the nickel and the aluminum alloys have a more hydrated, you can see the low value of oxidized oxide as opposed to hydroxide related chromium 3+ is lower here. So these two alloys are more hydrated compared to the one in particular with iron or with copper. And when we add iron, in fact, it's increasing the nickel concentration as well as the iron concentration in the alloy, which is quite interesting. Here are some polarization curves in 6 molar HCl for these for the solutionized alloys, and we see that indeed and this is the full immersion. We can see that we get this active passive transition for the nickel and iron alloys. These were terminated because of the limited amount of material, but indeed they didn't passivate as readily as the case for the nickel and iron alloys. So again, I'll just remind you that each of the subscripts here are the elements that have been used to replace ruthenium. Okay, so I'm just going to end it there. So I'll tell you that we were able to look at find these alloys with a wide single FCC region and region of chromium solubility. And the thermodynamic predictions here, the thermocalc database has been pretty accurate in what we find. They generally resist corrosion, pitting corrosion, although as well, but they're susceptible to crevice corrosion. They have a few nanometer thick passive film that has a mixture of all of these elements that are in the oxide, and the strong, very strong chromium cation enrichment was absent. So I'll leave it there. I think that's a good time to stop, and I'll take some questions.
Okay, thank you very much, Jerry, for an excellent presentation once again. And I think that also thank you for staying within the time limit that we've managed to catch up with the time now. So we're doing very well on that. And we do have plenty of time for questions. We have several here. Ayobame Daramola asked, notice when you substitute ruthenium with manganese, the configurational entropy is higher compared with others. Why?
Right. So I think that just had to do with the relative concentrations as we adjusted all of these concentrations to end up with a wide range of passivity. It's just the amount of each of the elements was more balanced in that alloy. I don't think there's anything too magical about it. Thanks for that.
Okay. Mario Jose Bueno asked, thank you for the presentation. Did you guys measure the hardness in the solutionized alloy? And what about the phase? It remains FCC after this treatment? Does it remain FCC after this treatment?
Yes, indeed. The alloys, thanks for the question. These alloys were indeed FCC, again, dendritic FCC structures as cast, and they solutionized to become homogeneous FCC phases. And indeed, as I indicated, if we heat treat at a lower temperature and quench, we get a range of interesting phases that are formed. So these are the as cast. You asked, did we measure the hardness in the solutionized alloy? Right. So the solutionizing decreases the hardness a little bit, but again the phase formation results in a strong increase in the hardness.
Okay. Jifty Opong asks, could you explain the mechanism behind the susceptibility to crevice?
Yeah.
And I should say after that, we have one more question, but I think we will have to stop after the next question. Okay. So.
Yeah. Okay. Well, yeah, so I think that the crevicing susceptibility is associated with the well-known mechanism of crevice corrosion, whereby any small gap can enrich in species more readily and reach critical conditions that are associated with that are required for breakdown at high applied potentials. So yeah, I don't think that, again, there's anything. Let me say that there are some very interesting aspects to these MPEAs or HEAs. On the other hand, they also largely follow our general understanding of corrosion and metallurgy. So these are the as cast materials. So there are, I didn't show you here, there are dendrites and coring associated with the solidification, and therefore compositional gradients that provide regions that are susceptible to attack. So I think that's what's behind it.
Okay, thank you. And a final question from Yangbing Ming. Why are the air-formed oxides dominated by chromium, while the passive film shows no dominant cation?
Yeah, another really great question. And yeah, I think that this really needs Kevin to
Yes.
answer.
Okay.
You know, to understand the fate of all of the elements, right? But indeed, you know, in the passive film, we have under passive conditions, we have elements that are dissolving out as well as enriching in the film, and we don't for these alloys fully understand that. Although indeed you might expect that you know that the oxidation, the air oxidation, which doesn't really provide an opportunity for the oxidized cations to leave the surface, that you might have more of a mix of the cations in the oxide, but that's not what we're finding. But you know, we need to do a full analysis to really understand that. So.
Extremely interesting. Okay, we are over time, so I'm going to pass quickly to the next person. I'd like to thank you, Jerry, for the excellent presentation, and for the three keynote speakers, John and Nick, for the excellent presentations. I think we are all enthusiastic now about these alloys. And we will move over to Dr. Junsoo Han, who is a graduate from my research group several years ago and has been working in the USA with Dr. John Scully's research group until very recently. And so now he is back at the Chimie ParisTech, working in Philip Marcus' group. And he will be presenting some of the work that he did in collaboration between my group and John Scully. So, Junsoo, the floor is yours.
Good morning, afternoon, evening, everyone. So good to see you virtually. I'm not in the nice lab, but I'm in the nice lab. So today I will, after this fabulous presentation from the professors, I'm going to present about some more technical aspect for these multi-principal element alloys. So mainly using this atomic emission spectral electrochemistry and coupled with impedance spectroscopy. And as Kevin mentioned, this work was done mainly when I was doing my postdoc at University of Virginia under Professor John Scully, and in the project with Professor Gerald Frankel and Professor Kevin Ogle. So why we want to combine this? Why we are interested in coupling this? So impedance, as you may know, and you may use a lot in your labs, that it can give us some kinetical information and dissolution formation type of information, as well as surface parameters such as capacitance, resistance, and sometimes we can estimate the surface thickness. And ISEC technique, which has been presented in several times during this afternoon here, is allowing us to measure the elemental dissolution rates as a function of time. So it's as a function of time concentration is in this case. And this shows generally really high resolution. So atomic emission spectroscopy is normally in the ppb level, and the mass spectroscopy is even lower than ppb level. And it has been demonstrated that quantification by this technique is really totally reliable, so that we can measure whether the thickness or how much cations are dissolved in the solution type of things, and quantitatively. So this coupling will allow us to have some elemental resolved dissolution kinetics, whether it's in the anodic or cathodic potential domains. And also we will allow us to distinguish the oxidation leading from directly from the surface forming the cations, or the dissolution occurs through a passive film formed on the surface. And also it can give the information of impedance contribution of each element, so that we can compare with the total impedance that can be measured by the conventional electrochemistry. So I will not go into detail on this slide because Professor John Scully already presented the principle of the atomic emission spectral electrochemistry. So I do want to mention here is that this specially designed electrochemical flow cell is connected to the potential state, which allows all kind of electrochemical measurement that we want with the in situ and quantitatively reliable technique. So I will skip this for the principle. It's not the first time, I mean, what I'm presenting now is the first time I invented. So it was tried from previous Kevin's student, Slava Shkirsky. They tried to do this coupling for a simple system, which is in case zinc, the open circuit potential. So on the left side, you are seeing the ammonium chloride at open circuit potential. Then you're seeing zinc dissolution shows a nice oscillation correlating to the oscillation of the total current density. So we can expect that this oxidation for zinc in this condition is direct formation of the cations. Whereas when we change the surface solution to the sodium chloride, we are now no more seeing this nice oscillation, which is in blue, zinc dissolution rate. Whereas we still, of course, we see the oscillation of the total current, which is in red. So in this case, what was proposed is zinc dissolution occurred through an intermediate corrosion product film, which should be zinc oxide or hydroxide. So we could distinguish different mechanisms of this simple system using this coupling. The other, a little more complex system, which I was working in the Kevin's lab, is zinc aluminum zinc binary phase in the alkaline solution. So this is the polarization curve of this pure phase in pH near 13. And in the cathodic potential domain, when we apply a constant potential, we are not seeing any dissolution, neither aluminum or zinc, which is in red and blue respectively. But if we increase to this intermediate potential domain, we are starting to see the nice oscillation correlating to the electrical current density. And this intermediate potential domain, that we can say that zinc and aluminum both dissolve actively with charge transfer mechanism. Whereas when we increase the potential to minus 0.8, we see this nice increase and decaying of zinc signal as a function of time, which means that zinc passive film is formed on the surface, and we no more see. It's still, there's some oscillation, but the oscillation was still really attenuated, so there's no more seeing. We are not really seeing the oscillation of zinc as clearly as before. Whereas aluminum still showed this nice oscillation. That means that we propose that aluminum dissolution in this case occurred through this zinc oxide passive film formed on the surface. So by this coupling with this binary phase, we can still do conventional electrochemicals impedance spectroscopy, such as Nyquist plot, and also we can obtain the capacitance or CPE parameters, constant phase element parameters with conventional impedance. And also we can estimate the thickness, which show the good correlation between the estimation from impedance and the ISEC mass balance technique in different potential domains. And also we can construct, as you can see on the right side, as the elementally resolved Lizazou plots, which will allow us to estimate the dissolution kinetics of each element. So before starting about the ISEC impedance for the multi-principal element alloys, I'm going to start a little bit of polarization curve, more conventional way of electrochemistry. So what you are seeing here is the conventional polarization curve with the current density as a function of scanned potential. ISEC technique can give us more information, elementary result. So this, so I forgot to mention, this is nickel, iron, chromium, manganese, cobalt alloy in 2 molar sulfuric acid. And we can have the information of elements. So we have how much is contributed to the total current density. So when we sum up, it doesn't really reach to this black curve, which is the total current density. That means there's certain probably oxide formation, or the oxidation charge did not contribute to the total current density. So when we take a closer look at this Tafel domain, I would say near J equals 0 potential, which is 0.33 volt, then I put down this sum of all elemental current densities and nickel as an example. And at this potential, we can extract the nickel dissolution rate, which is close to 5 microampere centimeter squared. And what is interesting for us is to compare with this spontaneous dissolution of this high entropy alloy. But I, as an example, I only show the nickel here. So conventional electrochemistry, of course, by definition, open circuit means we cannot really measure the current. But by this technique, we can measure the contribution of elemental dissolution rate converted to equivalent current densities. So it reaches to around the 6 microamperes, which is comparable to what we extracted from the polarization curve here, Evans diagram here. So I did this for these 5 elements. So it shows a nicely correlating relationship, which of course is not showing like a one-to-one relationship rigorously, but still in the good range. So this means that by this extraction, we can predict the longer-term corrosion spontaneous dissolution rate element by element. So that can be significant for understanding the corrosion rate for these complex and multi-element alloys. And to go a little bit further at this TAFL domain, we can also extract the information of TAFL slope each element. So here, an example of nickel is if you see on this slope, I mean the TAFL slope is around the 94 millivolt. So what's interesting here is normally conventional electrochemistry, we are not really able to define the TAFL slope in the, like a more negative to this current equals 0 potential. Whereas this technique, as you can see here, over like a 1 order, slightly higher than 1 order, then you can see this linearity of nickel signal. I mean, other elements were same. I just put the nickel as an example. And when we do the mass balance calculation for this case, so if assuming that there's no oxide formation at this condition, and this J delta could mean that this is the contribution of cathodic current. So in this case, we can construct a like a mixed potential theory for elementally basis, elementally resolved case, so that we can extract the corrosion current density for this system. So it also can be used for the long-term corrosion for these alloys. So speaking about the impedance, so this is conventionally we are measuring impedance spectroscopy, like oscillation of current and Lissajous plot. But by ISEC, you can we can have more information elementally resolved. So nicely oscillating in phase with this current density for this alloy. And also we can construct elementally resolved Lissajous plot for these 5 elements differently. So this is really elementally resolved technique coupling, so that we can have more information element by element. So I just sum up the Lissajous plot of all the elements here. And I try to calculate the TAFL slope using this Lissajous plot, elementally resolved Lissajous plot from this ISEC impedance. And as I previously showed you from ISEC Evans diagram, I also calculated the elementally resolved TAFL slope. So at least this nickel, iron, and chromium showed a really good correlation between these 2 different determination of the elemental TAFL slope. Now, of course, there are some like discrepancies, for instance, for cobalt, which shows quite different values, which for now, we think that is due to the like highly noise signal of the cobalt. It's kind of technical artifact. So by this, we can think that some of the features here you can see is in the case of iron, as reported in other papers using XPS or TOPSIMS for this same composition, not exactly same, but same elemental composition, shows selective iron dissolution in sulfuric acid, which could be explained by faster TAFL slope, lower TAFL slope of the iron. So in the case of passivation, when I applied a single potential at 0.6 volt, you're seeing this decaying of the signal, both element total current density and elemental signals, but we are no more seeing the oscillation. So in this case, we can say that in this case, elemental dissolution occurred through a passive film formed on the surface. So it's obvious that passive film formed comprised of chromium and nickel, chromium and iron, as you can see this nicely decaying signals of these 2 elements, so that we can estimate which element is contributed to the formation of the passive film, and which element is going through dissolved through this passive film by this coupling. And of course, we can do conventional impedance spectroscopy. This is just simplified circuit models in different potentials. So by this, we could say that there is like a double layer structure, which was also reported in many articles for this system. So we can also connect this conventional electrochemistry impedance spectroscopy with plus with the ISEC technique. So to conclude, with this coupling, it was possible to have the corrosion rate, elemental corrosion, spontaneously spontaneous elemental dissolution rates estimated by Isaac Evans diagram for these complicated alloys. And also we could obtain the elemental dissolution kinetics using the Tafel slope elementary result by this coupling. And also, as I showed you two examples of potentials, and one potential we've seen the nice oscillation. So that means the elements were dissolved directly forming the cations, whereas when we increase the potential to the passive potential domain, the elemental dissolution occurred through this passive film. So that's why we couldn't see the oscillation of elements during the impedance. And also by conventional impedance spectroscopy, we could expect that there is a layered oxide structure so that we can understand the interface and other details using the impedance. So this technique can be further used to understand the dissolution and passivation mechanism. Not only this, mainly for this multi-principal element alloys, but also other complex alloys as well. So I would like to thank you for this work was mainly performed during my stay in USA, in the Ohio State University and University of Virginia, and also supporting with Professor Kevin Ogle. So thank you, and I will be happy to take your questions.
Thank you very much, Junsoo. And we are very short on time now. There is a question, and I think we'll just limit it to one question because we're very short on time. So Sanjay Chaudhary asks, why is the dissolution current of iron lower than that of chromium and others in the passive domain?
Yeah, thanks for the good question. So I didn't really specify the curve there because that curve there is actually normalized curve depending on based on the composition. So actually, if I don't do the normalization, the current density of iron and chromium is quite similar.
Okay, so the data is normalized for the bulk composition.
Yes, that's true.
Okay, okay. Well, thank you very, very much, Junsoo, for an extremely interesting presentation and a very well organized and aesthetically pleasing, I should say, presentation as well. Next, I would like to pass the control over to Dr. Xuejie Li, who has recently graduated from my group and has since been working on high entropy alloys in collaboration with Northeastern University in China. And he is currently in the process of getting ready to move, I believe, to work in the research group of Jamie Noel in Canada. So, Xuejie.
Hello, everyone. My name is Xuejie Li, and I'm currently a postdoc researcher working with Professor Kevin. And it's my privilege to give this presentation today. And honestly, I feel quite nervous after these 4 excellent presentations before me, and your expectation probably have been raised up. So I promise I will do my best, and I hope you do get some useful information or at least something interesting from my presentation. So the time is limited, so let's just get started. So my topic today is about the spontaneous passivation of the Canton high entropy alloy in sulfuric acid. It's about the effects of nitrogen addition and dissolved oxygen. I would like to thank the organizer, MDPI, and I would like to thank the chair, Kevin Ogle, as well. This work was done in cooperation with the Northeastern University in China. So the objectives of this work is to study the spontaneous corrosion behavior after passive film breakdown for the Canton high entropy alloy at the open circuit condition. So we are interested in the open circuit condition is that despite most of the research about the passivation were carried out at applied potential, the real life corrosion, real life passivation, in practice, it occurred at open circuit potentials. So that's why we're interested in the open circuit condition. So we, in order to study it, we employed the elementally resolved electrochemical technique, namely ASEC. It has been introduced comprehensively by the previous speakers, so I will not go into detail. So with the help of ASEC, we can probe the fate of the constituent element for the Canton high entropy alloy. And I will show you in the following slides how the spontaneous corrosion behavior of the Canton alloy could be altered significantly by adding a small amount of nitrogen, and how these two alloys, the sensitivity changed completely to dissolved oxygen. So these two alloys materials we were using, they are Canton alloy with equimolar ratio cobalt, chromium, iron, manganese, and nickel. And the other one, we add 0.13 weight% of nitrogen into this alloy. And on the right-hand side, you will see the microstructure of these two alloys. It shows that after the nitrogen addition, it did not significantly alter the microstructure. So this figure is the first result. So there are two parts of this figure. In the lower parts, we show the dissolution rate measured as a function of time. So it's the sum of the elemental dissolution we measured by ASEC. And in the upper part, it shows the corresponding potential. So please note that this alloy was pre-passivated at 0.4 volt prior to the experiment. So we can see for the first step at the open circuit potential, we detected very little dissolution because the alloy was in a passive state. And when we apply a cathodic potential at minus 0.8 volt, we would like to remove the passive film by applying this potential, and we detect some dissolution. And after the passive film breakdown, we release the potential to open circuit, and we see the dissolution increased rapidly to a constant value higher than the passive state. So we can tell that the alloy was activated after the cathodic activation step and with no sign of repassivation. So during this process, what are the elemental behaviors? So with the help of ASEC, we can distinguish the individual contribution of each element, and they are shown in the figure. And with some simple calculation, we can calculate the congruent dissolution based on the dissolution of nickel, because the XPS results demonstrated that the nickel contribute little to the formation of the passive film. So after this calculation, we can compare the real dissolution and with the congruent dissolution. We can see that in the cathodic activation step, we observed that the real dissolution rate was much higher than the congruent dissolution rate. It implies that this is the passive film dissolution at this step. And after this step in the open circuit dissolution, we observed almost congruent dissolution for all the elements. And the same experiment was performed on the Canton N alloy. So we can see for this alloy, we can see a very different behavior in the third step. After the passive film breakdown, we observed a dissolution peak, and following by the peak, the dissolution reduced to a very low value. So this implies that the Canton N alloy showed repassivation behavior after the passive film breakdown. Again, what are the elemental behaviors during this experiment? So they are shown in the figure. With the help of ASEC, we can detect the individual contribution of each element. We did the same calculation for the congruent dissolution, and we observed the same results in the cathodic activation step. There was excess chromium dissolution, and it indicates the passive film dissolution. And during the second open circuit potential, we observed that the real dissolution rate of the chromium was much lower than the congruent dissolution rate. So it implies that chromium enriched at the surface during this step. So we attribute it to the spontaneous passivation of this alloy. So further insights into this this slide compares the dissolution behavior during the experiment for these two alloys. So we can see a clear difference between these two alloys with and without nitrogen. We can also tell this behavior from the open circuit potential because in the passive state, the open circuit potential for the Canton alloy was higher than Canton N. But after the passive film breakdown, the Canton N alloy, the open circuit potential increased and was higher than the Canton alloy. And also it corresponds well with the dissolution profile. So that we conclude that addition of nitrogen 0.13 weight% afforded the Canton alloy spontaneous passivation ability. So further insights into this phenomenon could be obtained by elementally resolved polarization curve in 0.1 molar sulfuric acid. So Dr. Han has introduced you this similar results. So this curve shows the conventional polarization curve via the black lines and overlaid with the sum of the elemental current detected by the ASAC technique. And we applied a cathodic potential at the beginning to remove the passive film. We can see on the left figure, we observe this cathodic loop, and we attribute this to a strong reactivity of the oxygen reduction reaction occurred at this potential domain. So it raised a question that how was the oxygen reduction reaction, the influence of this reaction on the spontaneous corrosion behavior? It has been investigated and will be shown in the next slide. And the most interesting part from this curve for us is active passive transition potential domain, and they are highlighted by the green area. So there are two parameters we can obtain from this curve. The first one is the elementally primary passivation potential. We can see adding nitrogen into this alloy, we lowered this potential for the Canton alloy. And the next parameter is the critical current element for passivation. And it is the highest elemental current in the active passive transition domain. We can see adding nitrogen lowered this current density for the Canton alloy. And in the lower part of this curve, we showed the individual elemental current for both alloys, and also shown the congruent dissolution elemental current calculated and overlaid with the elemental current. We can see for the Canton alloy in this active passive transition domain, the elemental showed congruent dissolution behavior. But for the Canton N alloy, we observed the surface enrichment of chromium in this potential domain. So in this slide, we investigated the influence of dissolved oxygen. As I said before, we are interested in its influence. So we varied the dissolved oxygen in the solution by bubbling the electrolyte with argon, air, and oxygen. They are referred to as the deaerated, aerated, and oxygenated solution, respectively. The first curve shows the results, the same experiment performed on Canton alloy in these three electrolytes. We can see when we increase oxygen, dissolved oxygen content in the solution, we increased the open circuit dissolution for Canton alloy, as well as the open circuit potential. And on the right-hand side, we show the results for the Canton N alloy. We can observe inverse results for the Canton N alloy. When we increase the dissolved oxygen content in the solution, we observed a decreased dissolution rate for the Canton N alloy. Although we observed similarly, we observed the increased open circuit potential. And what are not shown in this figure is that we observed excess chromium dissolution during the cathodic activation. And for the Canton N alloy, we observed chromium enrichment during the spontaneous passivation process. This implies that even for this such a complex alloy with 5 elements, the chromium was still the major component that contributes to the passivation. But as the previous speakers has in their presentation, they have said that we have some other options with the when we develop such kind of compositional complex alloy. For example, the aluminum titanium. But for this Canton alloy, the chromium was still the major component that contribute to the passivation. So this slide, the last slide, we can correlate the spontaneous corrosion behavior with the polarization curve. In this curve, we show the elemental current taken from the polarization curve for both alloys. And we can overlay this curve with the open circuit dissolution rate in all three electrolytes for both alloys. And we converted the unit into elemental current. We can see when we increase the dissolved oxygen in the electrolyte, for both alloys, we polarize it into a more anodic direction. But this exerts different influence on these two alloys. For the Canton alloy, it increased the dissolution rate. And we can explain this by the polarization curve, because we are, for Canton alloy, the potential was still located at the increasing side of the active peak. And even in the oxygenated solution, the potential was not high enough to pass the primary passivation potential. And for the Canton N alloy, we increase the potential, we reduce the dissolution rate, because the potential for Canton N alloy, they were all located at the decreasing side of the passive active peak. So when we increase the potential, we lower the dissolution rate. So here are the conclusions. When we add 0.13 weight% nitrogen, we decrease the primary passivation potential and the creative current density, thus afforded the Canton alloy spontaneous passivation ability. And the major driving force for anodic dissolution in 0.1 molar sulfuric acid for Canton alloy at open circuit potential is the oxygen reduction reaction. While the dissolved oxygen improved the passivity for the Canton N alloy, and the chromium is still the predominant species during spontaneous passivation of Canton N alloy. Thanks very much for your attention.
Thank you very much, Xuejie, for a very clear presentation. And
thank you, Kevin.
The floor is open for any questions. We have a few minutes before we reach the magic hour of 4 p.m. in Paris. If there are any questions, as I know the work very well, I will not ask you any questions.
Yeah.
Okay, there seem to be no open questions at this time. So I thank you once again, Xuejie, and I'd like to thank all the speakers and everyone who is present here today. So I turn the floor back over to MDPI. I believe that is Anna.
Thanks a lot, Kevin. To the best of my memory, I haven't been to many conferences where the last two sessions of the conference would be so impressive. I know that I'm speaking about the one that is going to follow. And you have done a great job of having such an illustrious list of speakers in this particular session, Kevin. So you do deserve great applaud and congratulations. Jerry, John, Nick, Junsoo, and Xuejie. So all these talks were of highest quality, and thanks a lot. Before we break, I just wanted to, because we have a good number of people right now, I just wanted to share a couple of things. I may be repeating myself for those who might have attended yesterday and day before. Each one of the streams of this conference will be turning into spatial issues. And the chair of each stream will be the guest editor. I'm pretty sure, Kevin, you know that. So may I request the presenters to kindly communicate with the stream leaders and stream chairs and get to know about the manuscripts. They will be made available only through through the stream chairs, not through the general website of the journal or conference, so that the stream chairs have some control in terms of whom to invite, whom to include, and so forth, because they have been instrumental in organizing their streams, and they have done a great job, as you saw the example just now. So you will be hearing just after the conference from the conference organizers and the two journals who are sponsoring the conference about the special issues, but information will be coming through the stream chairs. Just to let you know that MDPI 2 journals, that is materials and corrosion and materials degradation, are the sponsors of this conference. Materials will be publishing, materials which has impact factor of more than 3 would be publishing only one spatial issue, and it will be on the page charge basis, whereas corrosion and materials degradation will be publishing so many spatial issues depending on the number of streams that we have, and publications there will be free of charge. There would not be any paid charges for publications in corrosion and materials degradation. On that note, let us break, and once again, huge thanks to Kevin for pulling together such a great session. And I'm pretty sure, don't go too far away, the session that is going to follow is going to be equally impressive. I can assure you that coming sessions have great speakers too. So you will have great experience. Good, thank you.